Okay, so today we're going to do graphical models, and here's the most important question that we want to answer. Who came first, the chicken and the egg? But okay, so this sounds like totally corny and stupid. What you should, however, remember is that this is exactly the type of reasoning you want to avoid in graphical models. As in, well, you know, if you have like a directed arrow here and a directed arrow there, and you get this nice loop, and then you can employ philosophers for centuries to reason about it, and you're not going to make very good progress here. And the reason is that actually this directed graphical model, as it stands, is bogus. So never ever have loops. So if somebody ever later on at some point when you maybe work in industry tries to convince you that such a design is a good idea, yeah, at least you'll have a very nice counterexample. Yeah, unfortunately, been there, done that. So let's start with something a little bit simpler first. So this is about as simple a graphical model as you could want it. I mean, actually, there's one simpler one where you have one cause and one effect, but fine. Okay. So let's try to figure out whether you need to be smart or strong to graduate, right? I mean, given that you guys are all PhD students, you very clearly fall into the brainy category, but okay, let's not talk about PhDs, but just graduation, maybe with a bachelor's. And let's assume that maybe there are more people in general who are strong than smart. Okay, so let's make it 10 and 20% respectively. And, well, the thing is, being smart or being strong helps you to graduate. So I've just made up those entirely random numbers here, where I just claim that, well, if you have neither of those redeeming qualities, then you only have a 10% chance of graduating. Whereas if you're strong, then, well, maybe you get a sports scholarship and you graduate. If you're smart, likewise. If you have both, well, it helps you a little bit, right? So the question, therefore, then is, well, you know, if somebody graduates, what can I say about, you know, whether he's strong or smart, right? So let's just now make up some table, right? So, you know, assuming being strong and smart, you know, those two things occur independently of each other. So then this is the distribution of events of people who are neither and who are both, and, well, these respectively. And you get them by just multiplying 0.1 or 0.9 respectively with 0.2 and 0.8 respectively, right? So this table's all clear. I know this is very, very basic, but we'll actually get to see a whole bunch of surprising effects as we go through it. So I think it's important to follow this through. Okay? So our joint model over strength, brains, and graduation, therefore, would be a very simple model where I have, you know, the independent events for strength and brains, and then the outcome of graduation given strength and brain. Right? This is the joint probability distribution. So I've totally made this up. Okay, so now let's see what happens. Is everybody cool with that basic setup? Okay. So now...
What is that? What's the left? What's the show?
Okay, this is just the joint distribution, right? So let's say if you're neither smart nor strong, so as in if you're dumb and wimpy, well, that occurs with probability 0.9 times 0.8. Right, because with 90% probability you're dumb, with 80% probability you're wimpy, so multiplying those two out, well, the majority of people are dumb and wimpy. Okay. I know it's not politically correct, whatever. Flip it the other way around, it's politically correct. Okay, fine. Chances that you are exceptionally both physically and also mentally, well, it's 0.1 times 0.2, so that's 0.02, right? Of course, we all in the room are, right? And that's just, you know, what you have for the rest. So now, if I want to figure out something like, suppose that somebody graduates, what's the distribution of it being strong and, brainy? Right? So the first thing that I do is I multiply this previous table with that one, right? So I get these numbers. Okay, so flipping back, so you can easily see what happened. Multiply the left pointwise with the right. So this is dot star in MATLAB, if you will. So we get those numbers. Okay. Now these are basically the probabilities for the triple of events, namely dumb, wimpy, and graduated. And that's 7.2% of people manage to get this. And strong, smart, and graduated, that's 1.8%. And then there's 14.4 and 6.4% respectively who managed to get through with one of those two abilities. So now I can ask the question, given that somebody graduated, what are the chances that he has any of those qualities, right? And so now all we have to do is, this is simply Bayes' rule. So we basically take the joint distribution and divide by the sum over S and B. So I just integrate those two variables out. Right? In other words, that's this matrix divided by the sum of all the entries of this matrix. Right? Okay. Is that step clear for everybody? Sorry for going through that very, very slowly, but it's fairly fundamental, and we will then afterwards make this way more complicated. Okay, so we do this. Now we've renormalized to 1, and lo and behold, these are the probabilities that we see now. Okay, so given graduation, these are the probabilities that people are strong and smart. So the first thing to notice in this case is that now all of a sudden these variables are no longer dependent on each other, are no longer independent, right? Before that, smart and strong were independent random variables. Conditioned on the fact that somebody graduated, they are no longer that. I think there was a question?
No, it's just...
Okay, sorry. Any questions about that? So it's kind of funny where we have independent random variables, we observe the joint outcome, and all of a sudden these independent random variables are no longer independent, conditioned on the outcome. So sometimes people write independence as follows. A independent B, you write this as such, right? Now, I may have A and B independent on each other, but I'll get the case that A is not independent given C. Right? So this is slightly counterintuitive, but we'll see a lot more of those cases. And yeah, the corresponding graphical model is this one here. So when people draw graphical models, they shade the vertices solid if they're observed, and they're hollow if they're not observed. This is commonly what's done. Sometimes people write them with an extra solid circle and leave them hollow, but this is the more common way. So that's just a nice way of sometimes, getting the idea of a graphical model across much more easily, because if I write this, right, then this is a lot harder to parse in this picture. Okay. So I can obviously do a few more things with this. So I can ask, what are the chances that somebody is smart if he graduates, somebody that he's, athletic if he graduates, or then I can ask, things like what are the chances that he has one of these, given the other. And you can work through all those numbers by hand explicitly, right? And this is kind of painful. It's painful because you need to really reason exactly about which thing depends on what, and it's painful and slow, and it's really not easy to code up. So what would be kind of desirable is if there was a language, a description language, which would allow us to take pictures like this and then immediately read off algorithms for computing all of this. And so what we're going to do is we're basically going to look at how to write out, to specify this language, how to ask arbitrary questions. Because of course, maybe the next variable here, okay, so here's strength, here's brain, here's graduation. But then maybe you don't observe whether somebody graduated, but you observe whether somebody is a CEO. Okay, nice joke on the side. One of Yahoo's former CEOs pretended to have a degree in something that he didn't have. And then he became a CEO, and after that he very soon was no longer a CEO. So this is not an entirely made-up example. But joking aside, we would like to have a mechanism by which we can reason about this, right? Because, of course, usually you need to have some degree in something if you want to become a CEO. Well, of course, unless you work at Yahoo. Now, this is the nature argument of education, right? So you have certain abilities and they help you to achieve some goals. Of course, the nurture argument is, well, going to university makes you smart, and going to university maybe makes you strong. Because, well, if you go to university, you see everybody else working out, so you also hit the gym, and, well, you also hit the library, right? So, in that case, the arrows go the other way around. And maybe there's something called motivation that, will encourage you to do this, but in this case, you would basically have something like this. P of graduation, strength, and brain is P of graduation. Maybe this is an independent random variable that depends on something entirely different. And then maybe this is the chance that, you'll get strong if you given that you graduated, or maybe that, you get smart through that. So this is a different model from what we had before. The main difference being that the arrows now go the other way around. Right?
You're assuming independence of S and B given T, right?
Correct. So obviously that's not the case because there's a limited amount of hours per day that you can spend in the library and in the gym. And I'm totally ignoring this, right? So this is a ridiculously simplified reasoning here, just to make sure that this is actually all safe. Okay. And so now the interesting thing is that if I do this, then conditioned on graduation, these things actually are independent of each other. So in other words, I get this fun situation where I now have random variables, S and G, where I basically have that A and B are not independent of each other, but A and B are conditionally independent given C. Right? So, very different setup. The graph looks very similar, but I have exactly the opposite fact. Right? So, here, by observing the root cause of something, the effects all become independent. Okay. Where else did we have such a situation before? Banabas spent probably half a lecture on this. Any ideas?
What's the question, sorry?
So this is a fun model, right? Where else did Banabash already discuss exactly that type of model before? He spent ICA would be one. Very good. Naive Bayes, yes. Naive Bayes very much does this, right? Because basically the occurrence of each word is assumed to be independent of each other, given on whether it's ham and spam, for instance, right? Okay, I think we can pretty much skip about this part because we already saw the explaining away, where we have essentially random variables becoming dependent on each other, conditioned on the parent. And, well, you can basically do the same thing where you then reason about one. So this is just making things more explicit. Let's say the website's down. Well, first of all, if the website's working, you know that both individual services have to be working. On the other hand, if the website is down, well, what do? You check maybe the more likely one of the two. If this is broken, then you can be pretty sure that the other one probably isn't broken, unless you have a hacker in the system. Okay. So why would you actually care about this? Well, one of the reasons is that it's much easier to actually reason about structured sets of random variables. And more importantly, you need a lot fewer parameters to reason about this. So in other words, graphical models are a tool for statisticians to basically inject some of the prior knowledge of what they think the system should look like into the model. So if you do an internship or if you work with some real data, one of the first things you should probably ask the people who give you this real data is, how was the data generated, right? So you should try to learn as much as you possibly can about where the data came from, how it was obtained, what the underlying assumptions are, which simplifying assumptions they may be made or not. So before you even start attacking any of those problems with a statistical model, really sit down and try to understand exactly how the data is being generated. Because this will immediately tell you that type of structure. And so basically any of the structure that you can figure out by talking to the person who gives you the data, you don't have to learn statistically anymore. And this just means that you need a lot fewer parameters. So if you think about it, right? So there's a lot fewer numbers that I need to know. So let's look at this graphical model here. So maybe it's a database and the web server, so MySQL and Apache, the website, and here's the user action. And these are 4 binary random variables in this case. So this is about as primitive as we can make it. It's just whether the user buys something or not, whether the site's up or not, and so on. And so I would need 15 parameters to model this joint distribution over 4 random variables. Quick question, why do I need 15?
Because they have to sum to 1.
Exactly. So that's why I don't need 16. Quite often, conveniently, you parameterize it with 16 numbers, but they're really not fully independent of each other, but that's fine. Now, for the factorizing distribution, well, I need 1 plus 1 plus 4 plus 1. Okay, so where do we get those from? 1 for the blue one on the left, basically for the M node, 1 for the A node, because they are binary random variables. Now, for this one here, I need 4, because I have 2 states for M, 2 states for A, so I get basically 4 possible values that I can get this for, and each of them will parameterize W. And then for the U variable, I basically actually screwed up because this would be 2. Okay, so please correct this. But that's still a lot better than 15, right? It's not massively better because here we have 8 variables, whereas there we have 15. But once you start talking about a much bigger graphical model, these savings can really make a big difference. So they can make a difference between number of parameters growing exponentially versus polynomially. And that drastically affects the learnability. Of course, the catch is if you screw this up, you're going to be searching in a horribly wrong statistical model space. So there are some algorithms that will help you infer those kinds of structures. Again, first of all, you should really take a graphical models class. You should do that anyway. But besides that, this is where you will actually learn things like this. There are a couple of nice algorithms that use nowadays sparsistency to infer what's then called clique potentials and so on. So there was a recent paper by Wainwright and I think that's her name. I forgot, but it's basically one of Martin Wainwright's PhD students. I'm not sure about her name. This would be around 2014. And they proved that under fairly general sparsistency conditions, you can actually learn structures of graphical models. It's a rather pretty paper. Okay. Any questions about this so far? I know this is very primitive, and it sounds deceptively easy, but yeah, just bear with me for 1 or 2 slides, and it'll get difficult again. Okay. All clear? Good. So the obvious thing is no loops allowed, because yes, you never want this. So you either have P of egg times P of chicken given egg, or P of egg given chicken times P of chicken, right? Can somebody tell me how to actually solve the chicken and egg dilemma in a proper way? Not in the philosophical way, but how do you solve the chicken and egg dilemma?
Sequentially, maybe? Exactly.
You're spot on. So, because the chicken doesn't lay its own egg, right? And the chicken doesn't hatch from its own egg. So, it's basically chicken version 3 generates egg version 4, from which hatches chicken version 4, and so on. So you basically have not a loop, but you really have a temporal axis, so you really have a spiral, right? So this, right? So, and that's essentially why this is actually quite clean. So, of course, statisticians don't like drawing those squiggly diagrams. So they figured out a slightly less appalling notation. So now I'll quickly show you that notation. Have you ever heard of the plates notation? Okay. So plates are, for statisticians, what for loops are for computer scientists. It's just repeat. So the simplest thing that you can do is, if I have some variable x, well, actually let's start with the chicken. Okay, so it's the chicken. If I want to have a lots of chickens, like a chicken farm, we do this. So ci, I going from 1 to n. So now I have n chickens. They don't depend on anything. That's kind of stupid, because they probably depend on something externally, namely, you know, some hyperparameter alpha, which determines their breed. So conditioned on the breed, these are the chickens. Okay. So now, if I wanted to have chickens laying eggs, I would get variables EI. So what's immediately wrong with this model? Well, the obviously wrong thing is that chickens don't only lay one egg. So I really get not variable EI, but EIJ. This is now a nested for loop. And so since each chook lays a different number of eggs, I will have basically J going from 1 up to MI, and here I have I going from 1 up to M, right? So what we've just done is we've created a nested hierarchical model, and this is a nice graphical model. Okay. So this is fairly simple and quick to write something that otherwise you would have to draw this. Yeah, I guess you get the idea, right? This takes forever to draw. This is nice. If you need to code this up in LaTeX, there's a package called Tix. Learn how to use it. It's very useful, and you will hate it. Okay. So, but it's worth your time. For any graph or any diagrams, this is quite awesome. Yeah. Okay, good. So now we still haven't solved that problem. Namely, we have a time variable. So for that, what you typically do is you take a little bit of liberty with that type of notation. And you basically have arrows going in and out of this. So let's go to the single egg chicken again. Okay, so we have chicken CI, laying egg EI. And, well, we have many generations. And so now we need to somehow specify that this affects the next generation of chickens and eggs, right? And the way how people usually take this liberty is that they will then say, well, here is CI plus 1, and here is maybe EI minus 1. So this is how people typically write such a sequence. It requires a little bit of interpretation, so this is not so easy for a computer to parse directly and turn it into a graphical model, but humans get this quite easily. There have been some attempts made to turn that type of graphical models directly into code. The most notable of those would be probably bugs, or rather WinBugs, which I think really actually only runs on Windows. At least at some point it did. Yeah. So, this is actually a nice repository also of graphical models if you ever want to build a graphical models inference system and you want to benchmark yours against everybody else. This is a very nice place where you can find this stuff. Okay, good. So what I've now shown you is how to essentially get repeated structures for graphical models quite easily. Any questions about that so far? Okay. So now let's look at the more general object, right? A directed graphical model. So this is now not just 3 variables anymore, but now here random stuff can depend on some other random stuff, right? And so now you will probably need to look at least once or twice until you can establish whether something is a directed acyclic graph. Right? I guess everybody knows how to do this computationally to check whether something is a DAG. That something is a directed acyclic graph. So, I mean, this would have been essentially somewhere introduction to, algorithms. Basically, you could just do a reachability argument and you keep on enumerating things. And if at some point you can reach a vertex with a smaller number, well, you know your host. Okay. Now, here's the corresponding joint probability distribution. So I think we can all agree that this is a lot easier to get your head around than this, which is exactly why people use this. And essentially what you're just doing is you're assuming that the joint probability distribution is in such a form that each variable will only depend on its parents. Right? And that's kind of straightforward. So this is basically, if you engineer a big system that acts in some deterministic way, you may very well have exactly that type of structure. One of the nice things is that if you observe all the random variables, you can very easily just write the joint log likelihood. Right? Because I take the log of p of x, condition on some parameter theta, and now all I need to do is just estimate those things locally, then I put everything together and everything's great. So now, parameter estimation is very easy. I'm just assuming that I have some theta I and some prior over that individually, and I can happily optimize away. So if you have graphical models where always everything is observed, well, that's super easy, but also excruciatingly boring. Nobody ever does that. I mean, yes, you can, but it's not so exciting. Where things get a little bit more exciting is if you don't observe everything. Right? And we've actually already seen that before. So let me write out something that we saw before already as a graphical model with that notation. So remember clustering, right? So we had some parameters, let's say alpha, which determine the cluster ID. And that one's not observed. But then I have the xi's that are observed. Right. So this is essentially what we have with clustering, where we don't know the cluster membership as we draw the stuff. And now we have to use something called the EM algorithm to actually infer cluster memberships. Right. Looks quite similar to this chicken and egg problem, right? As a matter of fact, this is a clustering problem, right? If you never observe the chicken, but just observe the eggs, and you want to basically partition, how many chickens do I have and what are their parameters? Well, you get exactly this. More seriously, these could be, for instance, the words inside a document, right? You can do much fancier structures, and then you will get latent Dirichlet allocation. So this is closer to LDA. So in other words, we are looking at models that are not exactly entirely trivial, and you can get to those very quickly through some fairly simplistic reasonings. And of course, what we also have is that maybe not only the cluster distribution here is suitable, but also that I have some language model, maybe theta j. Maybe I have a whole bunch of those for different clusters, and then maybe I have some prior beta. So this would be a very common clustering model, except that what you would probably do is you would have alpha here. You would then have the cluster distribution, phi. You would then draw the cluster labels from that. And the only variable that's observed is this. And conveniently, you set your priors in such a way that it's also observed. Okay. This is something that people use even today. So what you can see is that we've gone from something very primitive to something fairly state-of-the-art. Well, it's not quite state-of-the-art, but people still published very nice papers about that in '98, so it's not too bad, with just a few lines. Okay. So now getting back to this, and we'll go through the EM algorithm in a bit more detail later on. You guys probably all remember how the EM algorithm worked, right? We basically came up with the idea that, well, let's estimate what the cluster probability should be for each individual object, and then use this instead of the, unavailable, not observed cluster membership, and basically optimize over the expected log likelihood. So that would be the M step. So the E step was, let's infer the cluster probabilities. The M step then was, let's actually optimize over this. That's exactly what happens here. So the best thing you can do is make Q for X missing to be the conditional probability P of X missing given X observed. So that's basically here cluster membership and these terms all here. And then you take the expectation with regard to these missing variables. You plug it in here. And so it's very similar to what we had before, right? Where everything decomposes, just that now we take expectations over the missing variables. So a couple of important variants on this. The first thing is that, and we actually already encountered this, we didn't really have an amazingly good handle on the joint probability distribution over all those three sets of parameters. What we really did is we came up with a factorizing assumption on these probability distributions. Right? Now, that simplifies things further, but it's of course less optimal. So this is sometimes called structured mean field. The other thing that you can sometimes do is, when taking this expectation here is really, really costly, right? You could just go and draw from that distribution here. And then replace the expectation with a couple of samples from this. This is called stochastic variation and actually gives you some of the fastest algorithms you can currently find. So this is essentially state of the art about 2 years ago. I mean, yes, reinvented, but still state of the art. So we will look at the math behind this in rather much more detail as we go through. But the intuitive thing to remember about essentially EM, or in this case, variational inference, is in the E step, well, you basically just go and look at the probability distribution of the missing variables given the observed ones. And then you use that distribution to go and match this, right? And you keep on alternating between those two steps. And this is a nice convex step, and this is also easy, relatively easy. Okay. Any questions about that so far? All clear? Okay. Was this? It's deeper than it looks. As in, people have gotten tenure for that. Okay. So what we did so far is we looked at directed graphical models. We saw some examples of explaining away. And we had the curious case where observing a child can make random variables dependent. In the other case, observing the child can make the random variables independent. Or rather, observing the parent. Okay. So now we're going to make this a little bit more structured. No, not that kind of dependence. Yeah, that's my problem. But so the first thing, so I'm going to go through 3 typical cases of how I can have a chain of 3 random variables, right? So if I have 3 random variables, 1, 2, 3, then if you think about it, there are really only 3 different ways how I can orient the arrows, right? I could do this. Yeah, okay, sure, I could also do this, but then I just flip it around, so that doesn't count. I could have that structure. Or I could have this structure. This is common parent, this is common child. This is a chain. We're now going to look at those three cases again, just quickly review them to see what the structure is. So if I have A, is the parent of B, is the parent of C, then if I observe B, well, first of all, what I would have initially is that C and A are not independent of each other, right? So that's just by construction. However, if I condition on B, so if I observe B, let's just plug in Bayes' rule, right? So I get this divided by that. I can now pull apart those two terms, right? And now I can see that also mathematically, not just intuitively, that conditioned on B, A and C are independent of each other. Whereas if I don't observe B, then I could actually just integrate this out if I wanted to. So let's just do that. Because P of A and C would be the integral dB P of, okay, C is the child, P of C given B times P of B given A times P of A. I get something that, yeah, unfortunately now cannot be separated. Well, there's nothing I can really do. So that's why this chain, this creates dependence between A and C, and this makes them independent. Okay. So I'm going through this also in detail because in case you're ever not sure, you can easily rederive this. Okay. Now the next version is the common cause, right? What's this guy here? So I have, A, B, and C is P of A given B, P of B times P of C given B. And so if I want to find out whether, A and C are independent or not, I just need to sum over B. And yeah, okay, again, it's a mess, and A and B depend. There's no obvious way how I can partition this. However, if I condition on B, then again, I get terms that, are P of A given B times P of C given B. Right? There's a quick question, why don't I need to normalize this? Right? By Bayes' rule, I would have to normalize, right? Why don't I?
No, you look at the joint distribution. You're just normalizing. It's just there, right?
Yeah.
Divide by PB and then they cancel.
Yeah. So the point is basically that they're already normalized, right? Because P of A given B, integral over A will already integrate out to 1. Same thing goes for C. So I can either do the algebraic reasoning as what we just heard, or I can do the lazy one by just, knowing that, well, this has to be proportional, and then just realizing, hey, my work's already been done. Right? Both of those arguments will give you that. Okay? So here we have, this was basically the case of, Brain and Brawn, right? And graduation. Where graduating from university could possibly make you smarter and stronger, right? So B is the graduation. So then the last thing, this has actually its own name because it's so counterintuitive, it's called explaining away. And this is basically where conditioning on B creates dependence. Okay. So those are the only three things that we can really encounter. Everything else is just a variant of this. So why did I go through this? Well, because there's something called deseparation, which is an easy way of checking for an arbitrary graphical models what depends on what conditioned on whatever else. And this algorithm is sometimes also called the baseball algorithm. Yeah. So basically, let's say if I have sets A and B of random variables, and I want to find out whether they're conditionally independent given C. So basically, I start with a vertex in A, and then I have to do that for each and every vertex in A. And I want to find out whether I can reach B while C is observed. And here are the transition rules that I need to do for this reachability argument. These are exactly the rules that we went through before, right? Chains, common parent, common child. And so for chains, we see exactly that, well, observing the vertex in the middle stops the dependence argument. Whereas if it's unobserved, then the dependence can go through either way, right? If I have a common parent, then, well, observing the common cause makes things independent. Not observing them leaves them dependent. Whereas likewise here, observing the child makes things dependent, otherwise it's not. Okay. And these are basically just the same rules as what we had here, but just for pairs. Okay. This is a rather neat diagram, courtesy of Sam Rovweiss. It's always a good idea to print out this diagram if you ever need to look at graphical models and look at independence. So before exams, this is kind of handy if you print it out, right? Not sure whether it occurs in this class, but maybe in a graphical models class it might occur.
Did it stay actually on the right side?
Pardon?
So how are we going to interpret the first column? Corresponds to independence.
So,
independence.
well, look at the first row. Look at the first two. It goes on a per row basis, right? So the top two are essentially this graph.
I understand. I was considering the first column rather than also.
Well, no, I mean there's nothing meaningful in this column except that we observe things and here we don't. That's the only commonality, and I just would have run out of space.
The lower left corner develops the independence. Right?
Well, no, exactly. So basically, here, well, okay. So look at this. Ignore the rest. I mean, the only reason why it's grouped this way is that here we have observations and here we don't. But these two graphs really belong together, right? So they have nothing else to do with that. And this is exactly observing the common child makes things dependent, otherwise it doesn't. Well, this is like, well, you observe a child, you can make some inference about the parents, right? Maybe the parents were smart, right? Or maybe if you observe the child being very smart and one of the parents being dumb, well, must have come from the other parent, right? Okay, sorry, not politically correct, but whatever. Yeah. Likewise here, essentially this just means that you keep on searching back. So, whereas here if you observe that, if you have a child, then you just stop that graph traversal. So the good thing is this can be easily coded up, which is what matters if you want to do this algorithmically. So let's actually do this here. So the question is basically, okay, we have a graphical model, some model, and I want to find out whether x2 and x3 are dependent on each other given x1 and x6. Okay. So just by squinting at it, what do you guys think? Are they dependent? Are they not? And if so, why?
Dependence.
They're dependent. Why?
They have a observed common child. X6.
X6, yes. Does X1 do anything about them? Well, actually, that would make them independent, right? If we didn't have that common child, right? Because observing the parent makes the children independent. Okay, now let's see whether the algorithm actually works. So ball starts out with, going from X2 to X4, terminates there because that's an unobserved child. It goes to X1, well, nothing really happens. But then the path going to X6, right? That one goes through. Here it terminates, here it just carries on. So, I know this was kind of fun.
How did it go through?
Well, because this transition here, because it's a common child, means the arc can go through. Now here, it's unobserved in a chain, so it goes through, so I can reach X3. Right? So this is a blocker, right? Because it goes from child to observed parent. Here goes from parent to observed child to another parent. So this was exactly that rule set that we looked at before, right? Just this is really mechanically applying this rule set and working through this graph here.
So the key is not to observe your children.
Fun?
The key is not to observe your children.
Exactly. But to observe your parents.
If you would have observed X5,
Then
it would be independent.
Then it would have been independent, yes. Yeah, because actually if you think about it, this already makes X3 independent of the rest. You observe the parent, you observe the child, while also actually doing any inference about X3, I can do that regardless of the rest of the world. Yeah, good observation. So for instance, okay, so let's say, X6 is not observed, well then this also stops, right? Then I can just, get rid of this. And I actually can get rid of this, so the only thing I really care about is this relation. Okay. Good questions. Any other questions about this? I'm going through it deliberately slowly because you've probably never seen graphical models before, and I want to make sure that you're reasonably comfortable with them afterwards. Okay. So, what I want to do in the next few minutes is to start thinking a little bit about structures. And we'll do a lot of that later on. So, what we've already seen is plates. So basically the way of having a parent and many children is to have this plate, and this is of course how you would write the joint probability distribution. This is actually what we did a lot before supervised learning. Because, well, I have some parameter here generating maybe my patterns, my covariates. These are the labels. Now the labels depend actually on both the patterns and some vector W, well, on some parameter W. So for instance, in a support vector machine, all we were after was W. Quick question, why did I not care about theta in an SVM or a Gaussian process?
It's a discriminative model.
Exactly. Because for the purpose of inferring the y's, I don't need theta. Because conditioned on w and x, y is independent of theta. So this was exactly the independence reasoning from before. This is why you can throw this out. Can somebody tell me a case where this matters nonetheless?
Generative models like naive Bayes.
Yes, but like an application. Or basically a problem where this matters.
X is not fully observed.
Perfect. Perfect. So if I have missing variables in X, then it's actually a good idea to have a joint probability distribution, basically a model for all of X. And so then I still end up training my discriminative model for X and Y. And I will use my generative part on the X's to make sure that whenever I don't observe everything of X, I can get that.
So what exactly are W and theta in this model?
Oh, okay. So W is like, for instance, if I have f of x equals w dot phi of x, W is like the weight vector,
So it's the parameters of
the discriminative model.
discriminative model.
Yeah.
Okay. I was confused because I usually think about theta. as
Sorry.
parameters,
Yeah.
Yeah, it's the
We
underlying-
sort of kind of ran out of parameters to use for this discriminative part. So
And theta is the underlying distribution of x.
exactly. That's what you parameterize with that. So for instance, you could do something very simple. You could just have a simple mixture of Gaussians model for the x's, and then use that to infer what the missing variable should be. That actually works quite nicely. And yeah, of course, that's what you care. So now, something a little bit more interesting that gets us back to the chicken. This was really a Markov chain. It's actually a slightly more complicated Markov chain because I have two different types of variables in each step, right? I have the chicken and the egg, the chicken and the egg, the chicken and the egg. Now, here, this is essentially, if I at some point interrupt that chain by having omelette, that's the end of the chicken coop, right? This is essentially the assumption that, the future only depends on the present, which, depends on the past, and so on and so on. And because, statisticians are lazy, they write this as a plate as we did. Quick question. Some historians always claim that the future depends on the past, not just on the present, right? Okay, how can you rewrite that model into something like a simple Markov chain? So, and joking aside, this actually has a couple of rather nice applications. Okay, so this is our run-of-the-mill Markov chain. Right. Here's the present. Here's the future. Here's another future. Now, the claim that the future depends on the past, how would I first of all draw this? How would I need to modify this graphical model to make that statement true?
Arcs from past to future.
Perfect. Could, for instance, do that. Right? So this would be a Markov chain where maybe I look back 1 year. If I have a lot of memory, then maybe I'll look back 2 years, right? And sorry, this is not going to be on the video, but yeah, okay. So first of all, let's add those, and then you would go and add even longer arcs, right? And you keep on doing this, right? So, and this starts looking really ugly. And basically what I've drawn is first order, second order, third order Markov model. That's how they're called. So, okay, let's remove this again because it looks too horrible. How can I turn this back into first order Markov model?
Extend the definition
Of the present. Exactly. So what I can do is, okay, let's just call those variables here xi. We're no longer historians. I could have some variable zi to be xi minus 1 and xi. Right? If I do this, I now in those new variables zi plus 1, zi plus 2, and so on, I can very easily write it again as a first order Markov model. Okay. Where else does this thing occur besides, well, history?
That's how like LSTMs work.
LSTMs do that kind of, yes. They do actually a lot smarter things because they have a hidden state. You're just already one slide transition ahead of me. Good one. Where else does it occur? You've implicitly used that model in the past 10 seconds. All of you. At least all of you who were paying attention. Probably also the ones who were on the computer or on the phone and reading stuff, right? So, where else does it occur? Okay, what am I producing to teach you stuff? Language, right? So, I'm not just throwing a bag of words at you because that would be really horrible and would be very hard to understand. I guess everybody's seen the bag of words upstairs on the 8th floor, right? So by the elevator, this is the bag of words model. That said, I try to be more coherent than a bag of words. So in other words, you would at least want to have something where a particular word depends not just on the previous word, but also, you know, 2 words before and so on. So such that you get a much longer coherent chain. Now, there are 2 ways how to model this. One is that maybe something is going on upstairs and I'm actually thinking something which is then producing the words, right? This would be assuming that there's some latent state and I think before I talk. And I could also be Zippy the Pinhead and just produce a random sequence of words that don't necessarily make too much coherent sense. And that would also be, you know, a language model. Except that maybe a slightly sad one. So, what we already have here is essentially, so in language models, you definitely want to look further back in history. Secondly, you can quite often assume that there's a latent state that really explains things much more nicely. And the reason for having this latent state is because the idea is that this latent state will actually explain things in a simple form. So if you think about it, in the case of, you know, maybe the stock market, knowing whether you're in a bull or a bear market, the various stock prices as you observe them will lead you to much different conclusions as to whether you should buy or sell.
Not necessarily.
Okay, so maybe you should become an investment advisor then. Tell me.
No, I used to work there. So, okay, so the point is, it's a martingale.
Yes.
And it doesn't depend on past. Well, whatever happens in the future doesn't depend on past. Because it's a Brownian motion.
Well, that's a reasonably specific assumption on, well, what you're probably what you're referring to is essentially Black-Scholes and then much fancier versions thereof of how the stock price will evolve. However, what you would assume is that you have certain macroscopic stock indicators or just economic indicators that are a latent state that will drive the overall model, right? And Well, at least every once in a while somebody tries to make money this way, and I don't know how successful they are at it. Okay. With language, it definitely helps if you have a latent state. Right. By the way, all those deep learning stock prediction models essentially also assume a latent state. We'll see what happens to them. Okay, so okay, it definitely holds when you have something like a user model for traversal through search results. So in the simplest case, this is essentially just modeling. Is the user even still looking at the results? This works very nicely for Google search results. It also works rather nicely for optimizing what the user wants to see on Netflix. Yeah, we just submitted that paper, and it actually makes users happier on Netflix. So maybe you'll see it in production at some point. Yeah, it's a graphical model. And here's the math that goes with it. And you can, so this is usually how in a paper you would talk about it. You'd have that plate. And then, for good measure, you also write out the joint probability distribution to make sure that any ambiguity in here is really properly resolved. Because sometimes you don't really specify those things anymore in detail. You just have an error coming out, and then it's kind of unclear. And this very neatly resolves it. So I need to start my chain somewhere. I have, xi plus 1 given xi. Then I have all those observed things. Yes?
Just about the plate, how you draw it. So how do you know if this has many parents, or it has? Or it
That's exactly what I meant with it's slightly ambiguous. And this is why, in practice, you will always want to have this as well in your paper. Because that is not ambiguous at all. Sometimes you even have the model presented in 3 different ways. A lot of Bayesian non-parametrics papers go this way. They draw the graphical model, they write out the distribution, and then for good measure they also write out a sampling model of how to draw from that. Also partially because sometimes in the sampling model you can discuss specific details on how to do it efficiently. So that's effectively why. And also to make sure that if a referee doesn't get 1 or 2 of them, maybe he'll get the 3rd one. Usually the sampling version is the one that's easiest to understand. And if you send something to KDD or www, you really need that. Okay. But you're absolutely right, it's ambiguous. Sometimes you also omit obvious things that, so for instance, you may have priors, and sometimes you omit the priors if they are not essential for understanding the model. You would not omit the priors here, because this is math. But here there's an impressionist painting. Okay. Factor graphs. We've actually already seen this, right? What was the name of that model that Barnabash gave it? ICA, exactly. So I have latent factors, I have observed effects. Mind you, there's no reason why the number of latent factors needs to be smaller than the number of observed effects, right? But it makes inference a little bit easier if it is. You could, for instance, have observed effects, click behavior queries, watch news emails, and latent factors being user profile, what's going on in the news, what the hot keywords are, and so on. You can actually iterate that multiple layers. And if you take Ruslan Selekutinov's class next semester, I don't know what he'll be teaching one, but if he does, I would bet a lot of money that he'll be talking about the restricted Boltzmann machine too. It's a really neat model. And basically what you do is you assume that these latent factors depend on something else and then you get something else. So you get something of this form. And yes. Okay, I guess you get the idea. And so on. Yeah. Yeah.
It's like a neural network.
Yes. And as a matter of fact, by now, this gets published in neural networks conferences as a neural network. So it's not an entire coincidence. It has more to do with neural networks by drawing this picture than with the actual math. But it's good enough to get through the reviewing process this way.
What's restricted that it doesn't jump over?
You could do that, but then it'll just make it even harder to infer. So one of the reasons why this is actually a rather nice model to deal with is because in the restricted Boltzmann machine, all these variables, bar the ones at the bottom, tend to be binary random variables. And now what you can do is you can actually very easily sample one, and we'll get to sampling in a moment, one of those sets of variables conditioned on the rest very, very easily because they're just binary independent random variables. So conditioned on everything else, these are independent of each other. And then, conditioned on this, these are independent, and so you can do very simple sampling sweeps through a graphical model and actually get very good performance.
Is there any direction?
In this case, yes. I just didn't want to draw 9 plus 15. Well, yes. So I just didn't want to draw 24 errors, but you could.
Why are they not conditionally dependent if you're observing a common child?
So, they in terms of, yes, but what I can do is I can sample some of those variables, and then if I conditioned on the ones that I've sampled plus the observations, essentially one layer conditioned on the rest of the world is independent of each other. Right. So how would you draw that in plate notation? Well, you could, for instance, have, x1i, x2j, x3k. Now I need a whole lot of them. And I do this. There's your restricted Boltzmann machine. And this just means all to all. And you can immediately see that this gets you to the limits of what you can do easily in plate notation. There's a much nicer notation, if you want to look at this, which actually hasn't made its way into graphical models. It might be worth a small note. There's a paper called Dryad. It's a systems paper. Really cool paper, worth reading. So I forgot the name of all the authors in there. Frank McSherry is one of them. This was essentially Microsoft's response to MapReduce, and then they screwed it up. As in, the system was very nice, and you could only use it with .NET, so nobody used it outside Microsoft. And by the time they open sourced and released it, it was a little too late. But this has a very nice semantics of how to write directed acyclic graphs. So you should look at that paper. Yep.
I didn't understand something. You said that the condition on upper and lower being observed, the ones in the same level will be independent.
Yes.
But that wouldn't that be against the observing child and the parents being dependent?
Well, let's go through that, right? So the issue is that if I have, okay, I think I need to erase some stuff. Okay. So first of all, let's assume that I have a parent and I have variables x1 and x2, and I have a child. So, first of all, yes, you are right. They are dependent insofar as if I wanted to write out the joint probability distribution, yes. However, if I just want to look at the likelihood, what I'll get is basically, so if I do sampling, then, yeah, okay, it's still dependent, you're right. Okay, okay, so I screwed up. Thanks. Good catch. Okay, so if you make it undirected, you can actually make this work nicely. Okay, thanks. Okay, so we already did the PCA ICA part. Right. Cocktail party problem. We've already done this. Okay, here's another case. And the reason why I'm showing you this is not so much just because of recommender systems, but also in terms of how you write this out. So so everybody knows the Netflix problem, right? So Netflix problem, basically, you and I watch movies and, well, we rate them, and maybe if our tastes are similar, then maybe, the movies that I watch will also be recommended to you and vice versa. So people sometimes look at this as a matrix completion problem, and that's actually really wrong because most of the entries are not relevant for most people. In other words, for me, probably My Little Pony isn't particularly interesting of how much I like or dislike it, whereas maybe for my daughter, this is more important, right? And maybe I don't care about all the movies that my daughter likes. So, but that aside, what I really have is I have a whole bunch of users. Right? They all sign up. I have a whole bunch of movies made in Hollywood or Bollywood or wherever. Then I have those ratings. Now, what I get here is something that I cannot do easily in code, but that I can do very easily in graphical models. I basically don't get exactly nested for loops, but sort of intersecting ones. Right? So I only have a certain subset of user and movie pairs for which I observe the rating. So this is also one of the reasons why when you code this up, you need to think a little bit about memory layout and efficiency and so on. And I think everybody's right now already looking at the time, so I apologize, I went over time. Let's go through the rest later. I'll just quickly wrap up with the point here that you will basically have a model where you have product over all the i's, p of all the user i's, product over all the j's, p of mj, and then I have some product over all the I and j pairs in the rating set, p of rij given ui and mj. Right. And this need not be the entire set of everything here, because for most user movie pairs we don't know how well they play with each other. So the easiest way to write it is something like this. Sometimes people write it a bit differently, but this is another one of those limitations of the plate notation. But if you look at any recommender systems paper, you'll basically see pictures like this. Okay, and then you need to worry about this in code. Okay, so thanks for your patience so far. We've done a lot of graphs. Could you please stop the camera? And I'll see you on Wednesday.